I still love that I'm like zoomed in on you, Arshia.
Well, we're zoomed in on you, like we see you on four screens here.
Oh no, I'm gonna just back up here.
Oh no, you look great. Yeah, I think we have yeah, we have 5 minutes more. So um in another 2 minutes I'll go outside and shepherd people in again.
Sounds good.
There's always a huddle around the cookies, so
Yeah, I'm sad. I'm missing cookies. I should have gotten some like warm cookies here.
to fit in, yeah.
Next year, next semester. I will come back next semester.
Absolutely, yeah. You're always welcome here, so
And likewise, we're so close.
that is true, yeah. Promised Eric is still there, right? Eric Rhodes.
Yeah, Eric Herbst is
Yeah.
still here.
Is he retiring next year or
I don't
no?
know. He has
Oh,
not
okay.
said that.
Okay, okay, yeah, sure. Right.
None of us know. Still going strong for now.
Oh yeah, yeah. I mean, he had
We just
predicted
celebrated
the
50 years of
oh
since his
my
PhD.
God.
It's amazing. Yeah. It was also his 50-year anniversary.
Wow. Coincidences.
Coincidences, life, all of the above. Movement. Oh no, then I'm going to kick the desk. I'm going to put my leg over here so then I just don't fidget.
Okay, I'll slowly just walk outside and call people in.
Sounds good.
Yes, yeah. Oh, Ilse, you're muted. We can't hear you.
Oh, sorry. Yeah, I'm quickly closing Slack because I have 16 Slack environments that, that I
Oh,
don't want to pop up, including our child's daycare has its own
oh
Slack.
no.
So nobody wants to see that Slack.
Yeah, so feel free to go back to sharing full screen whenever you're ready.
All right, I'm ready. Here, it's closed.
We have around 2 minutes left, so you can,
Are you going to stand up there for introducing?
yeah, I can pick it up. That would
You,
make
you've
sense.
got that mic, you've got a mic
Okay,
here. And please ask her to stop screen sharing for Q&A when she's done so that I
okay,
can show everybody else.
okay,
And I'll start the recording.
okay. Thank you, Thomas. So, Ilse, you can,
Mute. Okay.
perfect, perfect. Yeah, looking good. It's not 3 yet, but we're slowly, everyone's very obedient this time around. Okay. Hello, everyone. Let's get started. Today, I have the pleasure of introducing to you Ilse Cleaves, albeit virtually. She's promised to give us a fantastic talk. Ilse finished her PhD from the University of Michigan under the guidance of Ted Bergen, and then moved on to become a Hubble postdoctoral fellow at CFA, and is currently an assistant professor at the University of Virginia, jointly between the departments of astronomy and chemistry. Today, she'll be talking to us about imagining other worlds. Ilse, without further ado, take it away.
Thank you, and thank you all for having me here in this unplanned virtual event. Before getting started, I am indeed bummed to miss you all in person. Oh, can you see me okay right now? Because now I can just see myself.
Perfect.
Okay. All right. I hope you can see my slides. But yeah, I am bummed to not be there in person. Sadly, I took fall break a bit too seriously. I tripped over last week and sadly broke. I didn't lose my foot, but at least I just broke my foot. But hopefully I'll be coming back to visit next spring. Charlottesville is not very far away. We're only a train ride away. And if any of you would like to come visit us, likewise, please reach out. Yeah, so I am delighted to be able to give you a bit of an overview of the work going on in our group to understand sort of this wonderful diversity of exoplanetary systems that we're finding by studying the formation regions that they came out of, planet-forming disks or protoplanetary disks. And so to motivate this type of approach, here, let's do a thought experiment. So I would like for you all to take a second, and I would like for you to imagine a planet. If somebody asked you to think about what you would, in your mind's eye, see if you were asked to imagine a planet, what would you see? For my students, most of them say something like Saturn, because that's like the only planet they've probably ever seen in a telescope in intro astronomy. Maybe, they're like a little bit of a NASA junkie and you really love like looking at images of the beautiful swirling clouds on Jupiter and the beautiful weather patterns. But yeah, typically things pretty much close to home. If I instead ask you specifically to imagine an exoplanet, now I want you to think about what you might see. Maybe you see some fun artist's conception of some like fuzzy, maybe very artificially colored planet orbiting some, exotic star. Maybe you see lots of colorful marbles in somewhat unrealistic color palettes. You get the idea. Scientific artists have started getting pretty creative, right? Instead, if I ask you now something more specific to imagine a habitable planet, what do you see? Most of at least my students, see Earth. Maybe if you're like more of a, again, exoplanet aficionado, maybe you see some like global oceans on some distant water world with some like teeming civilization of sentient tube worms or something like that. But you kind of see something Earth-like, right? And frankly, if you ask most people, including astronomers, including my grad students, to imagine a habitable planet, that term pretty much in the mind's eye evokes a Earth-like state. And that's largely because that's our best example. It's our only example of a habitable, inhabited world. Now, this isn't, for lack of trying. Exoplanet research has truly exploded in the last few decades, going from just finding these amazing objects to statistical characterization of their populations, now to detailed characterization of individual systems. And one of the frontiers here is really figuring out what these planets are made of. What are their compositions? The compositions of their atmospheres, the rocky planets, solids. What are these planets made of? And a lot of work has gone into measuring this detailed compositional information, this detailed characterization of exoplanets. So, for example, finding the spectroscopic fingerprints of molecules in the atmospheres of planets with the light filtering through their atmospheres. Or in some cases, getting to watch these planets orbit their central star. In this case, the planets themselves being so luminous that their individual spectra can be characterized and modeled and compositions inferred. But the thing about these cases is that they kind of both happen to lie at the extremes. And that's not a coincidence. Most of our information about the detailed compositions, including the atmospheric compositions of exoplanets, are doable for the extremes. So either planets whizzing around their host star such that we can see their atmospheres and characterize their atmospheres through things like transmission spectroscopy, or planets that are so far away that we have a hope of correcting for blocking out the light from the star to see them. And so the zone of interest, at least for the sun-like stars, is this sort of in between, this really challenging zone. Here I included the water world instead of Earth, but you get the idea. Maybe we can have some overlap here with definitely with the M dwarfs, but you get the idea that this zone is hard. And this isn't going to change, in the near future either. So this is a plot from a decadal white paper here, just giving an idea for sort of what it's going to take to characterize the compositions of planets in sort of the habitable zones of other stars. And so depending on your level of optimism or pessimism, you get very different numbers. But if you say, in this case, take 10% of rocky planets have Earth-like compositions, like similar amounts of oxygen and methane in their atmospheres, how many planets would you have to observe? Around 30. And if just one of these has a favorable composition, the amount of integration time required to retrieve that one planet is we're talking about years of integration time. That's to find just one. So that's sort of even the next generation of facilities. It'll be really challenging to get compositional information for Earth, essentially Earth-like twins. Now, of course, this isn't to say we shouldn't do that. We should definitely still do that. But while we're on this sort of quest to look for rocky planets and sort of interesting chemical signatures of their atmospheres, we can also go on a parallel track. And this is sort of the approach my group takes. So while these novel discovery techniques are being honed, we can take this parallel track by studying their formation environments and taking a slightly rephrasing the question a bit, saying instead, are we alone? And rephrasing that question to being, are we unlikely or likely to be alone? Okay, so what do I mean by that? Well, more specifically, asking questions like, are prebiotic ingredients, in this case, thinking like water or organic material, things that form an Earth-like composition, are these commonly available in planet-forming disks? How much planet-forming potential is there in a disk? How much mass is there? Is forming a Jupiter common or not? And how important or how crucial were the various conditions that were present in our solar system's history, its cluster environment, the type of star we happen to be around, the fact that it's a single star, all these factors, how important were they on the way to getting to our planetary system and our Earth? So not an exhaustive list by any means, and a limited list with a focus on Earth, but you get the idea. So disks can provide a lot of information about these questions. So what my group works on is a few prongs, in these questions. So specifically, what I'll talk to you about today is how we go about wanting to understand how efficient is planet formation for a fixed amount of disk mass. We want to understand what is the variety of chemical compositions that planets could inherit from their protoplanetary disk, at least initially, and how well can we actually measure these compositions. And then the third one I won't have time for today, but this is another big effort in my group, is trying to understand what are the most essential physical and chemical processes that determine or affect the impact or the outcome of the planet formation process. Essentially, I say what stirs the pot? What's most important? Stellar variability, the cluster environment versus isolation, all of these different things. So what are the most important physical ingredients? This work is, I cannot claim credit here. I must give credit where it's due to my wonderful group of people. Some here have moved on, some are not yet pictured. I have never been able to successfully get all of our group together except over lunch, which I guess food is the great unifier. So you're looking at our lunch meeting here to say goodbye to Jeroen. And then this is, we work closely with the astrophysics and astrochemistry lab over here, Kathy Duke's lab at UVA. And so this is a wonderful team of people, of postdocs, graduate students, and undergraduates that really have made the work I'll describe possible. Okay, so the first topic seems really basic. It's one of the most fundamental questions of planet formation, yet it's one of the ones we know the least about. It is how much material do we actually have to convert into planets? For a specific disk mass, if we even are able to measure it, what's the yield of planets? What's the efficiency of planet formation? And how long is that mass around? Is there even enough mass to form a gas giant? And how much solid material is there to form like rocky planets, comets, asteroids, or the cores of like gas giants? So the last of those three questions is perhaps not easy, but the easiest to go about estimating. And so in recent years, there have been a number of surveys trying to weigh the disks, measure the mass of solids, at least attempt to measure the mass of solids through their millimeter wave emission. And so getting statistics on large samples, hundreds of disks, you find some interesting things. So Heis-Mulders in particular did this really nice study cross-comparing what we've learned about the solid reservoir available during planet formation to the planets that these disks are forming, essentially. So if you take all the solids we're measuring with ALMA and you take you cross-compare to the Kepler, the mass distribution inferred from the Kepler planets. Again, there's a lot hiding underneath there, assuming some metallicity, some, taking your gas giants and assuming some metallicity there, some core mass there. So the details are in Heis-Mulders' paper down here. But essentially taking what we would infer for the required solid mass to form those Kepler systems compared to what we see with ALMA here in red, you get an uncomfortable graph. The graph here, if you take it at face value, it would suggest that we need all the dust in our ALMA class 2 disks to be able to actually reproduce just the planets that you can find, that you observed. And that doesn't even factor in all the other planets that are unseen. So that's an uncomfortable, those two graphs are a little too uncomfortably close. And nothing, as we all know, nothing in nature is 100% efficient. So that can't be it either. Lots of solutions are out there, possible solutions. So planet formation may just begin much earlier where the disk is still being fed by its natal cloud. So maybe the mass reservoir is less limited than we thought. Maybe these ALMA class 2 disks are already done forming planets, or they've formed a substantial mass in planets. And so we're just seeing the dregs left over. That's another option. A third is, well, we know at least for big disks, like the ones up here, like the D-sharp disks, that there's a lot of substructure in some of these systems. And when you concentrate your dust, you then can hide a lot in optically thick rings. So maybe we're just underestimating dust mass with optical depth. You still see something else in the data that you can't kind of sweep away. Specifically, if you look at, this is from Carlo Manara's Protostars and Planets chapter, if you plot the disk dust mass versus the mass accretion rate of gas onto the star, you see a correlation between these two. And there's no reason there should be. Gas mass is what should be accreting, correlating with gas mass accretion rate, right? If we're talking about viscous disk evolution, these two, gas mass and mass accretion rate, these two parameters should be related. Dust shouldn't be affecting the mass accretion rate. So If it's just that planets have formed or dust is getting optically thick or we're hiding it in other ways, sure, those things can be happening, but they have to be happening at the same rate that we're changing our gas mass to keep the gas to dust ratio constant. And if we plot the minimum mass solar nebula on here, it's a minimum, so that's why there's an arrow to the right. You know, maybe we are up here and we're special, maybe we're more massive than the vast majority of disks, and these have all formed planets. But again, the same idea holds, that we need to keep our gas evolving at the same rate as our dust. And there isn't a great reason for that. So you might say, why don't we just measure gas masses? 99% of the mass of disks is in the gas mass. And so that's the most obvious thing to do next. And ALMA has been a powerhouse in providing stunning, high resolution views into mini disks. So over here, this is a reconstruction of the gas distribution in actual disk HD 163296. So it's extracted, pulling out the Keplerian rotation of the disk using the package disk surf, and then it has a nice grid on, so you can kind of see how the rings and gaps manifest in the surface density distribution. So I think this is just gorgeous. But ALMA, it's provided an incredible view of the gas of these disks. However, we're not actually looking at the total gas mass. We're not looking at molecular hydrogen, the thing that's going into our gas giant atmospheres. ALMA is observing these trace species, and their abundances have just not been very reliably mapped onto gas. Okay, so we do have certain tools in our toolbox to get at this fundamental quantity, the gas mass of disks. So this image here, this is from CO emission from the HD 163296 disk. And that's been the powerhouse molecule used to attempt to measure H2 gas mass. It's the thing we use for extragalactic, attempts to measure gas mass, the equivalent X factor essentially for disks. The challenge though is that disks are too chemically interesting. And so CO is already getting heavily processed, we find, into things like CO2, into methanol, into formaldehyde, and other species. And so CO doesn't seem to be uniformly abundant as we would want in a gas mass tracer. There's not really a reliable single X factor, at least not yet. The second just bypass gas entirely and just use the dust. The thermal dust emission from those millimeter pebbles, we can assume some sort of gas to dust ratio, something like a factor of 100 for the interstellar gas is frequently used. But as you all know, dust is rapidly in the process of forming new planets. So it is a time evolving mass tracer. It's doing its own thing. And so that isn't really the best tracer either. The third option, and in many ways, at least theoretically, the best option, is to take your molecular hydrogen and make it emit light. Give it a dipole and make one of those hydrogens a deuterium and get HD. HD, you can get rotational emission from, and from that, you can get your gas mass. The downside here, sadly, is there isn't really a current way to observe HD. Now, to give you a sense for why this matters and why this is so essential and why these different tools vary so much and need to be calibrated, on the left, I collected all of the literature values of anyone who attempted to measure the mass of a particular benchmark system, the nearest and most heavily studied disk of all time, TW Hydra. These are all the people for whom I could find measured a disk mass at the point when we wrote this Protostars and Planets chapter. Anna Miatello made it look nice here. And so from this graph, this is all just one disk, and these are all different people who've tried to use different data sets to get TW Hydra's mass. And from this x-axis, you can see there's a factor of 100 variation between all these different methods, some using dust, some using gas, some fitting SEDs, and all of the above. The reason that we need something better, we need something like HD, is highlighted here in yellow. These particular papers highlighted here, these 5 papers, all incorporate HD in their fitting process. And we can get to an accuracy of gas mass to at least sort of a factor of 3 and possibly better if we have information about the system, the temperature of the system. So this is a huge improvement. And HD itself is fortunately chemically uninteresting. It doesn't freeze out so much. It self-shields. It isn't highly chemically altered by chemical processes. It's a really nice tracer, if only we could observe it. It was first observed by Herschel, and so here, these are the reductions of the original data, but you can clearly see the 1 to 0 rotational transition and the 2 to 1 rotational transition. Beyond these detections of TW Hydra, only 2 more were detected, so we only have 3 disks where we actually have a decent handle on gas mass using something that's truly related to H2. And while these data, were truly revolutionary, showing us the gas, in disks like TW Hydra, the mass was substantially larger than we previously expected. These are spectrally unresolved. These are PAX observations. They're spectrally unresolved observations. And so all you really have is an integrated line flux from the disk, integrated all over the entire spatial face of the disk. So since then, we haven't really had sensitive enough far infrared, essentially eyes on the sky, to do this again. Our next glimpse of getting reliable gas masses, getting reliable planet forming potential will be as part of the ASTROS mission. So ASTROS is mainly an ISM physics type mission, but as a proof of concept, there'll be a couple of disks observed with high velocity resolution, TW Hydra being one, to see whether we can get spatial information out of the spectral domain. By resolving the spectral profile, can we see where the gas is coming from? And so we're hoping that this is a launch of late next year, 2024. And my student here, Amanda Alvarado, will be working on the inferring or unraveling the spectral domain into the spatial domain. Going forward, so the next mission concept proposal out there is as part of the NASA Pioneers program, is the Planetary Origins and Evolution Multispectral Monochromator that I'm involved with, or POEM for short. And it's another balloon-based mission, Antarctic balloon-based mission, where one of its key goals is finding or detecting HD towards a larger sample here, hoping to go improve our sample by an order of magnitude from 3 to more like tens, or like 30 disks here at high enough velocity resolution to unravel the disk. But this is, again, we're still talking tens. We don't have statistics yet. And so the next thing I'm really excited about is a mission proposal, also coming out of the ASTRO 2020 decadal, this recommendation for a far infrared or X-ray probe scale mission. So the probe I'm quite excited about, that's being proposed by, your own Meredith McGregor is here on the team, is the Far Infrared Spectroscopy Space Telescope, or FIRST for short. And this will take us to hundreds of disks. So we'll have actually a census of disks down to masses that can form something like our solar system. And the other benefit is it's not limited to a single balloon flight. It'll have a substantial guest observer component and a pretty flexible tuning as well. Okay, so great, things in the future, but what do we do now? We have a ton of data piling up in the ALMA archive every day. We have lots of gas detections. Can we use these to reliably infer disk mass? Can we calibrate the submillimeter emission from things like CO, which we otherwise understand really well in the interstellar medium? So to get at this question, we have the benefit that in the last sort of 10 years, right, we've been working very hard to improve chemical models to get more and more accurate in interpreting or measuring, measured fluxes, I should say, from facilities like ALMA, to interpret what molecules like these mean in terms of how they trace the X-ray luminosity from the star, how bright the molecular emission is, how bright the UV photon, the PDR region is, how deuterium chemistry is or isn't active and where, and so forth. Of course, with these chemical models, we quickly discover that there is no one-to-one linking of any molecule to any process. Sadly, we can't say, hey, N2H+ is our dense gas tracer or something like that. Instead, we know it's all highly coupled, as it is in all interstellar environments. But chemical models don't hide that complexity. And so one avenue my group is working on is understanding how we can use explanatory machine learning methods to unfurl this complex interdependent web of physical parameters affecting the chemistry we observe. This is a highly complementary approach to what we typically do, which is brute force large-scale grids of chemical models until we find a good fit, which is what the field has done for a long time. My graduate student, Amina Diop, is working on these kinds of efforts to try and calibrate CO to get our magical X factor to get gas masses from these sorts of observable molecules. In this particular case, she's working with a chemical model, just looking first at CO to understand how we can best understand the CO chemistry and all the different physical parameters it depends on. Amina's taking a pretty neat approach where she doesn't run a giant grid of chemical models, but instead she looked at a single chemical model and recognized that the densities span many, many orders of magnitude, the temperatures span orders of magnitude, the radiation fields span wide orders of magnitude, and they cover a wide range of CO abundances. And so she thought, there's enough data in here to train something on, to understand something. And so she built up a transparent regression model. And so the paper is going to be coming out soon. It's under review. We have some excellent reports and should be completed shortly. So you should see this soon. But the fundamental thing of it is that this particular model it's not trying to be the most accurate predictive model, but instead it's aiming to be the most clear explanatory model to tell us what affects CO the most significantly and destroys it or forms it, what processes lead to its destruction. And so her key findings, for example, are that dense cosmic ray radiated gas or dense X-ray radiated gas are susceptible to destroying their CO, carbon monoxide. And the carbon monoxide is more robust in warm environments. Now, these aren't actually new findings. This is what people have found in the past with these large grids of models. But the beauty of this is that Amina was able to do this with a single model, discover these same results in a fraction of the time in models that take less than 30 minutes to run. And so you can take more complex molecules and do a similar analysis, figure out under what circumstances do organics get destroyed, or when is water formed. So I'm looking forward to seeing which ways we can apply this next. So essentially, to summarize this portion, one of the most fundamental parameters of disks, the disk mass, is one of the least constrained ones we have, but it's fundamental to measuring so many important parameters. The potential for planets to form, how many planets can form, the efficiency, how do you convert gas mass into planet mass, and timescale. They didn't get into this, but if you can measure the mass of many systems at many evolutionary stages, we can learn whether TW Hydra is indeed an outlier with its gas mass hanging out into the very late phases, or if the more common timescales for giant planet formation really are as limited as we've thought historically. All right, so the second part of my talk is to discuss not just the potential of how many planets can form, but what they can form with, what compositions are possible. So within these disks, we know that they, have this dust mass, they have gas, and they also have ice. And we know that this material is not uniformly distributed throughout the disk. And so we want to know, what are the compositions of disks? Why do they vary? And do they change in time? And at what point do the compositions kind of get locked into planets as well? Those are some of the questions we're interested in. So if you take a cross-section of a disk and you look at the gradients of temperatures and densities, like I said before, you get a wide variety from hundreds of Kelvin to maybe 10 Kelvin in the outermost disk, and densities spanning something like 10 to the 12 parts per centimeter cubed up to 10 to the 8 parts per centimeter cubed is typical of a disk. So you have a lot of range. You get many different distinct chemical environments associated with all these physical environments. And so we want to know, how do these get incorporated into the planets forming within them? The solid component into those terrestrial planets or into the cores of the gas giants. Now, this isn't a new idea. So it's been proposed that since the temperature is dropping as you move further away from the star, molecules are freezing out as you get further away. As you cross certain threshold points, these so-called snow lines, we expect the composition of the disk to fundamentally change with distance from the star. And so there was an exciting idea here led by Karin Oberg that if a planet forms at these different locations, they'll fundamentally have different compositions. And so these should imprint in exoplanet atmospheres. And this was exciting because at sort of a similar time here, it was realized that yes, we could, from the transit spectra of exoplanets, the spectra look fundamentally different when you change your carbon to oxygen ratio. So we should be able to extract this information out of exoplanet atmospheres. And if we could measure the C/O ratio in the atmosphere, maybe we can say where that planet formed in the disk. So that's the sort of overall hope and the hope for all desire. Of course, while snowlines definitely still exist, ALMA has shown us that disks are truly physically and chemically dynamic objects. We have our snow lines here, where material like water, CO2, and CO freeze out. But on top of this, this overall picture, there is this new element that the dust is this little, is this transport or this mixing substrate that can provide some connections between these different zones. So what do I mean by that? So if we have our disks, the vast majority, we see some evidence of settling, of growth of grains and settling out to the midplane. Some of this dust then is transported inward, and maybe some of it is trapped into pressure bumps and rings. If these dust grains are coated with volatile ice mantles, you could have little transport vehicles, essentially, of transport of volatiles throughout the disk. You could redistribute your volatiles throughout your disk, bringing water to the innermost disk or other species. And so this has been a big question. How much does this actually change the chemistry of the disk? The recent ALMA MAPS large program led by Karin Oberg showed that these disks, all of which contain substantial amounts of substructure, have extremely different compositions. The top row here, all the same molecule if you compare the scale bar at the bottom on similar spatial scales. All of these are the same molecule, but observed towards 5 different disks as labeled at the top, and they're not the same. Some have distributed, in this case, cyanide chemistry. Some are very compact and only a compact ring. Some are centrally peaked. So it's the same molecule, but it looks completely different depending on the system you look at. If you then instead hold constant the star, HD162296 again, but look at 5 different molecules, you see a similar story. You see, okay, there's distributed CO, rings of HCN, but then you take this other CN-bearing molecule over here, and it's only a single concentrated. Over here, formaldehyde distributed, but doesn't peak towards the center. So again, if a planet forms at any variety of locations in this disk, you'll get something completely different. And going disk to disk, you see something different as well. And that's just a few of the molecules observed in MAPS. This is the gallery from the ALMA MAPS info website. So all of these 5 disks are the targets of ALMA MAPS. And then across each of these columns are different molecules. And there just truly aren't patterns. Like sometimes you see a ring pop up, but sometimes it's totally different in a different disk. Okay, so is there any rhyme and reason to this? Are there relationships between these different molecules? This is TW Hydra again. Are there relationships between the molecules, or maybe with the molecules and various substructures in the dust? That's the next question. And Charles Law, this wonderful analysis, attempting to figure out the answer to that question mathematically by labeling all of the structures, all of the rings and features in the disk, and he attempted to look for commonalities. So I don't know if you can see on your screen, but each of these is a molecule and a molecule, same axes on the right-hand side. And this is 1 star AS209, lower mass, and then intermediate mass star. This is HD163 again. And there's the structure and the structure. And so white here is molecules that have similar patterns. Blue is molecules that don't. And if you just take parts of this graph, you could stare at it forever, but I won't make you stare at this forever. But just one thing to point out is if you look at the bottom left corner here, for the intermediate mass star, there's sort of similarities between these cyanide-bearing molecules and the CO-bearing molecules, but at the same zone on this graph, these are some of the least similar molecules. So even disk to disk, there aren't even regular patterns between the two. These trends seem to be elusive. There might be some relationship between centrally peaked continuum and organics, but that seems to be about it in terms of quantitative information. Now, taking it back to comparisons with exoplanets, for this sample, plus a couple of others from the literature, We have attempted to measure C/O ratio using the various molecules observed in these disks that are C/O sensitive, like the hydrocarbons are particularly good at this. And so using these models, we have attempted to back constrain C/O. And so from the ALMA data, you see the lines are roughly where the numbers are. So a lot of times the observations are pretty low resolution, or we have to integrate over the entire disk. So that's why you see a large bar rather than nice little fine points or something. But the main takeaway here is that for many of these disks, we see C/O ratios consistent with even as high as 2 because of their bright hydrocarbon emission. Some of these other disks down here, calcium 15 and IM loop, maybe 1, but still pretty high. How do these compare to exoplanets? Well, the most closely related, or at least spatially closely related planets to compare to are these direct detection exoplanet atmospheric compositions, which all look kind of solar in their C/O, and they're different. They look very different. The ALMA disks look much higher. The innermost disks, so only a few have been measured so far. So here are the exoplanets, 1, 2, 3, 4. So here's some range and the references down there. But here are the disks. GW loop was JWST observations of Sierra Grant, and AA tau is previous Spitzer observation. So there's some range. There's some more overlap between the disks and the exoplanets for the inner disk. So maybe that's doing better. But yeah, for ALMA is consistently very high. The ALMA observed chemistry seem to be inconsistent with directly imaged planets, at least today. Yeah, more overlap here, but not so much here. And it's not like we can just say, hey, these ALMA radii have nothing to do with planets. You know, they are so far out that it's not the same gas, because it's where the bulk mass reservoir is. This is where most of that mass going into giant planets actually lies. So we have to look at this gas. So the next question here is there actually tension between these disks and the planets? It's a pretty small sample over here. So we need a larger sample of representative sources to actually know whether these two things are in tension, disks and exoplanets. Unfortunately, data are incoming. We have the new ALMA large program, the Disk Exoplanet C/O connection. We tried. It was a little bit of a stretch, probably one of the worst acronyms I've been involved with, but it's DECO for short, and we have a great Art Deco logo. So I'm very proud of this guy down here. It is an ALMA Cycle 9 large program to try and use essentially toolbox small species to trace the C/O ratio as well as gas masses towards a much larger sample of 80 disks with roughly 40 to 50 AU resolution. So we'll know whether the inner disk is distinct from the outer disk or not. And so here's our lovely, team of co-PIs. And our toolbox molecules here are CO, N2H+, and C2H, this wonderful hydrocarbon. And while these graphs are a bit complicated, the thing I want you to take away is here on the bottom-most graph, for example, a factor of 3 change in the carbon to oxygen ratio changes the flux of this key hydrocarbon by 3 orders of magnitude. It's highly sensitive to the C/O ratio in the gas. And then we can use this ratio up here of CO over N2H+ to trace the carbon to hydrogen ratio and many, many more different molecules in our spectral setup. But so these are the workhorse ones. And this is our wonderful team. And so our team, spans actually here on the next slide, many different continents, countries, an excessive number of time zones, makes scheduling telecons especially challenging. More than a third early career students and PhDs across our collaboration. And fortunately, sometimes we get together here. This was from earlier this year, our first DECO team meeting here at NRAO Charlottesville. All right, so what DECO is doing is we sampled, we took previously detected millimeter bright disks down to a minimum inferred gas mass of about a Neptune mass of gas of sub-Jupiter. And the disks span some of the 4 best studied regions, Lupus, Taurus, Ophiuchus, and Chameleon. Within each of these regions, we have 20 disks, and we divided them between the M dwarfs, 10 M dwarfs, and 10 future solar type stars. And this was intentional to try and get the most common exoplanet mass star hosts. We also spanned our sample over disk extent, making sure we had both compact and extended disks to see if that matters, if there is some impact of radial drift of the transport of solids. And we had to cover our lines using 3 spectral settings, so there's a lot of exciting bonus science. It's 150 hours of element time here. So we'll get things like a wide range of deuterium to hydrogen, NHCN, possibly also C2D. We'll localize small organics. We're going to get a lot on sulfur. We have a bunch of CS and SO detections already. And if you don't like chemistry and you prefer physics, we will have some of the most accurate stellar masses. It's hard to get stellar parameters directly from these young stars. They're hard to fit using classical methods, but we have a gas disk orbiting the star, so we'll have a pretty good concern on masses from the gas kinematics. And looking for, non-Keplerian motions, we see already some filaments feeding some of our disks as well. Okay, so you still might say to me, well, cool, lots of data. You're going to go find some cool molecules. All right, what does this mean for planets? What about all these planets that we're going to be mostly seeing orbiting very close to the host star within the terrestrial planet forming region in the inner few AU? What does this ALMA data tell us? Well, just to reiterate, this is not an isolated environment. You have this transport coming in from the outer disk, filtering into the inner disk. And so understanding this whole ecosystem is incredibly important, knowing what the outer disk composition looks like and the inner disk. And then the neat thing is that the inner disk chemistry with current and upcoming JWST observations is going to be characterized pretty in amazing detail, and already has been characterized in amazing detail through MIRI observations, specifically MIRI. So these were early models done by my former postdoc, Dr. Dana Anderson, aiming to look at how the inner disk gas varies in its composition with its C/O ratio. And so she used various progenitor molecules to attempt to see if we can see the history of the gas that flows into the innermost disk. And the long and short of it is that sadly we cannot see the history of what molecule formed, what molecule traveled to the innermost disk, because the innermost disk is a pretty chaotic and destructive place. But on the positive side, we can very accurately detect or measure the carbon to oxygen ratio of that gas. And these different scenarios of pebbles settling and drifting and moving inward, whether it's well mixed, settled, or maybe starved, the inner disk is starved by some kind of radial structure, they all have extremely different predictions for the carbon to oxygen ratio of the inner disk. So if you have some measurement of your outer disk, your inner disk, and these are the Karn-Oberg's C/O classical plots on the background, you get incredibly different predictions from deficits to enhancements there. And as of cycle 1, 18 of the DECO targets will be observed with MIRI at high sensitivity. And in cycle 2, we're getting 22 more, and we'll have complete coverage of all of our torus and our lupus disks. So I'm very excited about that. That'll start in January. This is the kind of quality of data we'll be getting. So this is Sierra Grant's recent paper. This is part of the GTO program over here. So this is part of the MINDS program here. And so even this data are so sensitive that we can see even the 13 CO2 emission. So this is sort of quality we're excited to get. But I don't have a ton of time, it looks like. So I'll move on a little bit faster. So you might ask, all this talk about the gas, what about the solids? You were talking about terrestrial planets and habitable worlds. Who cares about the gas? And so what are we hoping to see? So my current postdoc, Dr. Nick Ballering, took our chemical models and made this amazing realistic post-processing of our data using spatially dependent opacities with a really cool technique adapting k-means algorithms to sort of group opacities in our models to make them efficiently run through RADMC3D, and made these incredible predictions for ice observations across the spectrum, but also including JWST. And we should be able to see things like the CO ice feature popping up at very deep depths of the disk. But then as you go higher up, you see different species both get a bit weaker up here. Now, those are unresolved. The next frontier here is if we can actually see the distribution of ice and if it changes in time. Does it depend on the degree of substructure or not between these sort of 3 different scenarios here? And we are also excited, and I'm sad to not be there in person because I was really looking forward to talking to Julian about this new data that we recently got or was taken with JWST NearCam in coronography mode. to try and localize the water ice in our disk. So the idea of this experiment is that there's a particular system, B4046 Sagittarius, unsurprisingly aligned with our galactic center. So there's lots and lots of background stars behind it, 50 actually. And so we should be able to look for ice in absorption against the background stars and in albedo, scattered light from the surface of our disk. So this is where the gas disk extends to with ALMA. And these are known background stars with BLT sphere observations. So the third part of my talk, which I'm not going to go through here, half of what my group does is we want to understand how the energetic star shapes and alters the chemistry of the broader disk. How do energetic processes relating to ultraviolet, X-ray, cosmic rays, all these different processes shape what happens within the disk? Because otherwise this disk is just a big cloud of interstellar gas. You know, there's nothing else exciting going on. The star is what does all the fun stuff. And so my graduate students here, I just wanted to highlight the wonderful work they're doing just briefly. Rachel Gross working on understanding the cluster environment, how it alters the chemistry of the disk, especially with UV photons from the outside, and also with new laboratory experiments. Abby Wagoner is going on the job market this year. So she's in her final year of her PhD, working on understanding how bright X-ray flares shape the composition of the disk. As well, creating bursts of water, for example. So she had a paper recently out with the MAPS collaboration. And then Daryl Long is conducting an amazing survey of how ionized midplanes are, like the localized, planet forming zone, how much active chemistry actually is happening in the midplane versus is frozen in. And on the cluster environment side, I also wanted to highlight this recent paper by Nick Ballering as well, showing for the first time clear resolution, clear destruction of the proplids. So seen previously here, in the beautiful HST images, now with JWST, he got ALMA band 3 data where we can clearly resolve the arc of the hot gas blasting off the surface of the disk from external photoevaporation. And so previous VLA observations saw the hot gas, previous ALMA observations found the disk. He found with this beautiful, very high resolution ALMA data, he could split the two apart and for the first time split the disk from this arc directly and get accurate disk masses. Okay, so while understanding the planet forming potential and the potential compositions is interesting, I understand that it doesn't tell us whether there is a habitable planet in that system or will be a habitable planet in that system one day. It's definitely not the end of the story. Even after the disk dissipates, there's plenty of things that can happen. Geological effects, atmospheric effects, stellar effects, all these things are going to affect the final outcome of whether habitable planets can form, of course. But by getting a more realistic understanding of how planets start, we can start to also understand and model these later stages much more accurately. And over the last decade, we've really discovered planet formation is truly a complex physical and chemical process. But this last 10 years have given us the chance to really improve our models, and data have been rapidly improving as well. And these in-depth studies of disks, like the MAP survey disks, for example, have truly honed our models such that we can really understand what's going on small scales. And so now the field is really moving into the statistical or population type era. For example, HPRO is another survey I didn't get to mention today, but also DECO. And having a better understanding of the disk, both the physical structure of the disk, the temperature, the mass, all this stuff, plus the composition, can also help us feed or get better ideas of what could happen through things like planet population synthesis models. We can get some statistics on planet distributions that are much more realistic than what we've had in the past, both for planets that we can observe and those we can't. And that would be useful just to know in the future to help us better choose candidates for systems, for stars, to more carefully follow up in the future with once these kinds of Earth-like planets are more observationally accessible. Let me say it that way. And at least for the time being, by seeing the compositions that are possible in disks, we can think a little bit more creatively about what planets can possibly exist, can be. All right, so thank you all. Well, thanks to my group first, of course. Funding agencies would not be possible without them, and all of you for your attention and coming for an unplanned virtual talk. Thank you all. And here are my bullet point slides. All right, thanks.
Thank you so much, Ilse. Questions in the auditorium?
Hello, this is Bryce Bullen visiting from Goddard Space Flight Center. It's a very nice talk you gave. So I'm coming from a solar system perspective. I study asteroids and comets, and one thing in particular that I'm interested in is in the CO content of the original planetesimals. My question for you is, what is the closest in you have seen CO to its star in a exodisk system?
I muted myself, and then when you started talking, everything disappeared. So I think I'm back. The question was, what is the closest, like between the star and the disk composition we see?
What is the closest, if you've seen like an ice line for CO? What is
The closest in? The closest in we've seen an ice line. So for what, if you're thinking about water, for example. Water, there are some, constraints that put it at a few AU, but it's hard to tell if we're seeing the midplane versus if we're seeing the surface snow line, for example. For carbon monoxide, we've seen it come into something like 20 AU for TW Hydra. But in other systems that have same solar mass as TW Hydra, they're both about a solar mass, TW Hydra maybe a little bit smaller. We've seen CO snow lines out to like 50 AU for IM Loop, for example. And that's just because that particular system, the mass we think is there. That one doesn't have an HD measurement, unfortunately. But we think it has a very, very massive disk. And so it's basically like a giant brick, and it's extremely cold. And fundamentally depends on the disk structure. I don't know if that was the question you were asking, but that is an answer to a question.
No, that's a great answer. Thank you.
We have a few questions online, so I think Guangwei had the question first. So Guangwei, please.
Hi, this is Guangwei. I'm working on exoplanet atmospheres. So as everyone knows, the JHU deadline is coming up in a couple of weeks. So I'm trying to do a hot Jupiter atmosphere proposal, and I dig through all the archive in the last year, all the published, JHU spectra and what's the inferred CO ratio. And it seems like all of them are below 1. Does that mean like all the hot Jupiter form kind of within 10 AU-ish, but can we really say more than that?
That is a great question. So the other way in which you could get that low of the C over O ratio is if you form your planet in a different way. If you don't have a core accretion formed planet, if you have a planet formed by a gravitational instability of a very massive disk. Now, we haven't really considered this in the past because all of those disk masses I showed you earlier, they were so low that it was thought, okay, all these disks are totally stable against gravitational instability. Their masses are extremely low. And so we didn't worry about it so much. But I think now that given that we have a couple of these HD measurements of disks that suggest they're all actually much more massive than we previously thought, i.e. the CO was under predicting the amount of mass that was there because the CO had gone into other carriers. Yeah, it's possible that that is another opportunity. I feel like I'm not claiming planets are forming via gravitational instability, but I'm just saying that's another way to get a C over O ratio that's as low as that, as part of the is similar to the stellar composition, essentially. I should say that for these young stars, actually directly measuring the stellar compositions is like almost impossible. So there's one person, Mikhail Kama, who has attempted to actually measure like stellar composition versus disk composition, mainly for the primarily radiative Herbigs, the more massive star disk systems. But he's done some more detailed characterization of star disk comparison. But yeah, to get that low of a number, you could also say that here. I've got to figure out how to share screen again. Blue Jeans is a new thing for me here. So bear with me. Can you see my screen here?
Yeah.
Okay,
Yeah.
so yeah, so you could get like even sub C over O low if you had maybe formed your hot Jupiter after a major pebble drift event, possibly. So here, this would be ice pebble drift with an oxygen enriched inner disk. So that would get you even as like 0.35, like a lot of gaps in the outermost disk. You could raise your C over O ratio of your inner disk to like 1.2. I don't know if
Yeah.
that yeah, gives you some ideas. And I'm happy to share this later if you send me an email.
Yeah, sure. Yeah. This is just most in the past year, all the GFC resolve hot Jupiter, they're sub-Jovian mass, so it'd be hard to form from collapse, gravitational instability.
Oh, okay. So if they're that small,
They're
that
low
is
mass, yeah.
interesting. So that might be
Relatively low mass.
suggested that pebble drift is the key then. If they're that low mass, yeah, then there you go.
Yeah, I think direct
Cool.
imaging is all the high mass ones. The transiting
Yeah,
ones are all low mass. Yeah. Cool, great, thanks.
thank you.
I have another question online, Katie.
Yeah, so my question was quite similar to Guangwei's, which didn't surprise me at all. We work closely together. Thank you so much, Ilse, for a great talk. But in the case of, how skeptical are you when exoplanet astronomers just report, the C to O ratio, and this means this kind of planet formation? And would you like us to stop until you understand this plot more?
Wow. Would I like you to stop? No, obviously not. Please keep reporting things. Maybe don't make, hard claims about where they formed because, again, like the C over, as you can see here, there's like 3 different radial profiles of C over O. And if you plotted them, I originally plotted these all on top of each other and it was such a mess. So like radius of, I don't know, take 5. And depending on what happened in the disk's evolution, you could have 1.2, 0.6, or 0.9. So you can have the whole gamut depending on what happened in the disk beforehand. So I think that we want the numbers for sure. We might rather than trying to say it formed at a specific radius, I think what the disk field is interested in right now is like, what does the outer disk look like and what does the inner disk look like? Can we at least say something about that, given the complications of everything in between? So yes, so please keep reporting them. And for the values of the C over O ratio, just I think that we similarly are using models to fit spectra. And models have all of these implicit assumptions. And as actually one of the things the activities of the DECO team is we are bringing together there's 5 different codes contributing to creating our conversion factor from our line fluxes to our C over O in mass. And we're doing the cross comparison against all of these 5 codes from like Japan, Leeds, Virginia. It's just we're covering a lot of different in the Michigan group, and so we're covering a lot of different code bases to see what the intrinsic error is in our ability to even just turn spectra into physical parameters, and we're hoping to actually fold that into our when we provide our values, the uncertainties in our values at the end of the day. So I'm actually I'm glad we're doing it. I'm also terrified because I'm afraid we're just going to give everyone a giant scatter plot of C over O with error bars covering the entire plot. But we will give you what we find as best we can measure it. So similarly, I hope the exoplanet community does the same for us. We just want to know the truth.
Sounds like a great plan. Thank you.
Other questions in the room? Thank you for also touching upon the models and their uncertainties, because throughout the talk I was like, what models is she using? Seems like she's using everything.
Yep, we are using, we have our own, time-dependent chemical kinetic style modeling like many of folks in the community. But yeah, we're discovering just in this cross comparison, like, oh, your mean molecular weight is this and that. And how do you assume external radiation reaches the midplane or doesn't?
Right.
What directions are you calculating extinction for? Just simple things. And it's been actually really cool because the cross comparison, we've discovered how like other people are doing things in better ways than us. And so we've improved our code, they've improved their code. It's just been an amazing cross collaboration that was unexpected. We were just expecting to like have this nice survey of 2,000 data cubes, a lot of data cubes just from the Alma side. And now we're having this great modeling discussion too of like modeling and uncertainties and how can we improve these.
So can we look forward to a mega chemical code?
A mega chemical code. Well, I don't know about that. I think that that's still a little bit further away since we were trying to understand, transport dynamics, mix like all these other, and like if we need to actually start calculating the chemistry while the disk is still embedded in the envelope rather than starting from some T of 0, like, oh, the disk appears, time is 0, right? I think there's still like a bunch of questions there, but we're working on all of these pieces to see what matters. So yeah, maybe, but not out of Deco, but like, once we get a better handle, especially, with the JWST data coming in, we'll know more about like how important is transport, which there's hints that the disks that are compact do seem to have really interesting, like more oxygen-rich inner disks compared to some of the disks that have large gaps in the outer disk known from ALMA seem to be like volatile poor. So there's like clues that weird things are happening due to substructure. But yeah, I can't say more than that because it's low number statistics still, but there's interesting features, yeah.
If there are no other questions online or in the real world, then I'd like to thank you again for taking time off and meeting with us.
Thank you all, and I hope to see you in the spring, physically, without a broken foot.
Thanks so much. Have a great day.